Already. For this video, we are going to read this GitHub page about how to debug your battery. And oh, come on. Okay, what's happened? Oh, we are still recording. Okay, I don't know what that was, but I feel like we are still recording. Yes. Okay. Anyways. So this was from Hacker News, and my knowledge of materials science and just basic chemistry is very limited. Not basic chemistry, but like undergrad chemistry is very limited. I've never taken any undergrad chemistry courses, but we are going to see how much of this we can understand and how you debug your battery design, I guess. I guess this is design, so it's probably a lot of mathematics, so that's how you can debug your battery design. Alright, so this is from a company called ionworks. Let me see what my cousin is doing. Anyways, so ionworks is build and run battery simulations at scale. Alright, so these guys are doing something interesting, I guess. Backed by Y Combinator. And what is the pricing? Run simulations in ionworks cloud. Access full library of models and parameters. Free credits per month. 0.01 per additional credit. Community support. Okay, so 1 million credits. Share results with team. Alright, so I guess this is a very fun thing that these guys do, and it's backed by Y Combinator, so I don't see why not already. Okay, so now let's take a look at their news. ionworks partners with iontra. Our 2023 Why is parameterization so hard? ionworks presents at the International Battery Seminar. Physics-based models. Okay. Guess we can. Okay, and then let's see who the who the founder is. Tom Trantor. Chief Technology Officer of ionworks. Waterloo. It's pretty solid. University of Leeds, University of Warwick. I'm not sure where that is. That sounds like something in England. United Kingdom. Fair enough. And he's been at the Faraday Institution. He's been a researcher at UCL and a senior research scientist at National Physics Laboratory, and now he's at ionworks for a year and 6 months. I'll check my messages later. Anyways, how to debug your battery design by Tom Trantor, co-founder and CTO at ionworks. N.B. I have edited the title to emphasize this is more a theoretical exploration of battery design than practical advice to fix your hardware issues. Sorry to disappoint those coming for the latter. More a theoretical exploration. Okay, that makes sense. Picture this scene. You are an engineer at an electric vehicle company, and your boss comes to you and says, Jeremy, we've got a problem. Your name is Jeremy, by the way. Sure. It's these damn batteries. There's just too many of them in the car and it's weighing us down, but we really want our customers to be able to drive 400 miles without having to stop and charge. What do you do? How do you debug your battery? It's a black box of magic, right? Wrong. You can use simulation. The end problem. It seems like there is no good solution in the market today. Batteries are either designed to be high energy or high power, not high energy and power. We stick a bunch of high energy batteries in the vehicle. High energy and high power. Okay. So that means you have batteries that can hold energy a long time, or you have batteries that can discharge energy not for a long time, but more aggressively, I guess. If you stick a bunch of high energy batteries in the vehicle, we might get more range, but then if we stick a bunch of high energy batteries in the vehicle, we might get more range, but then we try to accelerate, they overheat because the rated power is too low and the losses in the system are too high. This causes us to over-engineer the cooling system, adding weight and cost, and we also find that batteries operating at higher temperatures lose capacity faster. Also, there are other constraints on the battery design such as safety, lifetime, weight, and last, but by no means least, cost. Below is an indicative spider plot of the main metrics that battery engineers tend to care about when designing or selecting cells, which often compete with one another. So they care about fast charging, they care about high safety, you have to maximize safety, long lifetime, low temperature, high energy, low cost, high power. So basically high energy is low cost, it's not that safe, it has long life relative to these guys, and it's low temperature most of the time, more than these guys. But when you want original, well, not sure about original, he didn't mention that, but high power is fast charge, high power, not very safe, not very long lasting, not very low temperature, not high energy, and it's more expensive, but you need something to accelerate. Alright, a good intro into cell design can be found by batterydesign.net. Below is an image taken from that site of the difference between high power and high energy. Thinner electrodes tend to be better for drawing larger currents because there is less material in the way of ion transport, but they have more inactive material. In an example, current collectors and separators, the gold, gray, and yellow bits per unit volume, making them less energy dense. Okay, below is an image taken from the side of the difference between high power and high energy. Thinner electrodes tend to be better for drawing larger currents because there is less material in the way of ion transport, but they have more inactive material. Current collectors and separators, the gold, gray, and yellow bits per unit volume, making them less energy dense. I don't quite get this, but thinner electrodes, I'm thinking if you have like AAA battery, that's thinner than AA battery, and that makes it better for drawing larger currents because there is less material in the way of ion transport, but they have more inactive material. So you have more wrappings per cell, per electrode if you just have thinner electrodes. Kind of makes sense? Intuitive. This problem is even bigger for your body designing. Oh, that's Jimmy. Jimmy, right? Or Jeremy? Jeremy. This is where the cell is side. Okay. We skip. This problem is even bigger for your body designing batteries for electric aircraft, as the peak power needed for takeoff and landing is much higher than the power needed for cruising. So you have to prioritize and sacrifice range. Aircraft also find it really hard to top up charge mid-flight. For great perspective on the prospects of electric flight and required performance metrics for the battery, I recommend this article and this article. Luckily, you know an engineer at your battery supplier and you can call them to discuss the problem. The curse of dimensionality. The battery supplier is well aware of the difficulties in designing batteries and explains they have been spending years on the problem, testing different designs, trying to optimize for different use cases. It takes at least 1 day to build and fully test one single design in the lab with all the characterization experiments they need to run and up to 1 month for cells selected. For accelerated aging tests, this is where the cell is cycled really hard constantly, and the data collected is then extrapolated to a real-world driving scenario, car mostly parked on your driveway. But going from one scenario to another isn't so straightforward as the aging effects are non-linear. A rough estimate for how much it costs to build and test a new battery design on a single cell, one data point, is around $1,000. Oh wow. The battery supplier is well aware of the difficulties in designing batteries and explain they've been spending years on the problem, testing different designs, trying to optimize for different use cases. It takes at least 1 day to build and fully test one single design in the lab with all the characterization experiments they need to run and up to 1 month for cells selected for accelerated aging tests. This is where the cell is cycled really hard constantly, and the data collected is then extrapolated to a real-world driving scenario. That might not sound too much, but now consider how many different design decisions go into making one battery. You have to choose materials, the anode, the cathode, electrolyte, separator. Makes sense. I guess I remember this from chemistry 12, chemistry 11. Yeah, okay. Each solid material can be tuned by thickness, porosity, amount of space for solid active material or for liquid ion transporting material, particle size, composition if a mixture of materials. Then you have geometric factors like form factor, cylindrical, prismatic, pouch, size, number of taps, current collector thickness, safety features like venting cap and central mandrel. Each these are a lot of new things. Not a lot, but for me at least, for someone who's never ever read anything about battery design. Anyways, each electrolyte composition can be altered too. This is often where the secret sauce actually is. But maybe more on that another day. Let's say conservatively, there are 20 things you might want to change. If you collect 3 different data points, changing each thing one at a time, original design, some number high, some number lower, while keeping everything else constant. Usually a good scientific approach. That's 3 times to 20 possible combination of changes. Because you have... Oh, he already gave us the 20. It's not these guys adding up. Anyways, the show script below illustrates the cares for a 3 variable problem. It's hard to visualize a 20-dimensional parameter space, but you get the drift. And did we get the drift? Import MATLAB and just for having that points line go from 0 to 1. 10 mesh grid, it's 1 by 1 by 1, is it? Mesh grid, and then he's showing the curse of dimensionality, that you have one more dimension, it just grows exponentially. Now testing 3.5 almost billion batteries is obviously a ridiculous thing to do, and no reasonable battery developer would carry out that many experiments. Even if you parallelize by say 1,000 and have a huge test facility cycling batteries constant, that's still over 1 million experiments for each cycler channel, which would take at least 1 million days and cost over $1 billion. What if you reduce your number of days and we go up to 1,000 days and $1 trillion? That's doable, I guess. I mean, it doesn't work like that. I know. This is known as the curse of dimensionality. The more things you have to vary, the exponentially more combinations you have to test. And unfortunately, battery engineers have this curse pretty bad. In fact, several battery unicorns are spending basically all their money on R&D as they're trying to bring their new technology to market without having yet put a single cell inside a single car. Okay, so we have these crazy battery R&D unicorns. How are you a unicorn if you don't have a product? I don't get this, but sure. The solution to the AND problem. So AND problem was either high energy or high power. You can't have both. Your battery cell design. Okay, yeah, stupid. Guess would be, why can't we have both of them at the same time? He's gonna probably explain that. Your battery cell designer has some hope for your problem, though. They have been testing a new material which could deliver more energy density while retaining high power. An anode with a mixture of graphite and silicon, this being Silicon Valley, and all you are pretty excited as there must be plenty of that around. And yes, when can you get some batteries to test out? So while retaining high power, anode with a mixture of graphite. Okay, okay, well, your battery supply says we're still evaluating that material. It might be a little while longer. The initial tests in the lab look good, though. There are already some cells on the market with silicon, but we've had a few issues. More on this in a bit. Typically, the cell designers won't actually be making all the modifications and carry out all these tests themselves. They will have their own suppliers of materials, and they will be doing a lot of tests too. Let's take the anode as an example. The anode is the negative electrode in the cell, host ion in what we call the active material. Think itty bitty particles. The lithium ions intercalate, which basically means it squeezes inside the crystalline lattice of the host material, and this causes the material to change in size. Once inside, a process like diffusion occurs where ions migrate to the center of the material, a spherical particle for the sake of argument. As the concentration of lithium ions inside the host material changes, we call the lithiation, filling up with lithium. This is an electrochemical process and requires electron transfer to take place, which occurs when current is supplied or drawn from the cell. Here's a great and easy to understand video by limiting factor on how batteries work at the particle and atomic levels. I'd say this is a good video. Tom probably he knows what he's talking about. Yeah, let's give it that to him at least.
Welcome back, everyone. Okay. I'm Jordan Giesecke, and
maybe not that right now, but here. Let's continue with the article. Adding silicon to an anode gives more capacity to the cell as there are more host sites for lithium per unit volume, but this does have one or two drawbacks. The first is what happens to the cell voltage. Okay, voltage hysteresis. There are typically several stages of the process of lithiation where the crystal structure tends to form stable phases as the degree of lithiation increases or decreases. The chemical potential of the lithiated particle is directly related to the degree of lithiation. Hard to measure, and this basically translates to the open circuit potential or voltage of the material, easier to measure. Without okay, I'm not getting this, so let's Google this guy. Hysteresis refers to the difference in voltage levels between the detection of a transition from logic low level to a logic high level and the transition from a logic high level. Okay, so goes up or goes down. I mean, that's why he said voltage, because it flows from one state to another. Without diving too much deeper into the physics, we can safely say, as you charge and discharge, ions move in and out of the host material and voltage changes. The voltage changes more slowly when materials are changing from one stable phase to the next. Careful analysis of the open circuit potential and its derivative with respect to lithiation or capacity, dV/dQ, the rate of change of voltage to the rate of change of capacity. Alright, I'm not sure. Can then reveal what the material inside might be, because crystals are somewhat predictable. They have characteristics plateaus in voltage at certain degrees of lithiation. On the flip side, if you know the material, you can predict the state of charge from the voltage. Something the battery system designers really like to know. I say somewhat because silicon unfortunately suffers from voltage hysteresis, meaning that the voltage when charging and discharging in a cycle follows different paths even when cycling very slowly. So one cycle is like one whole discharge and charge. It sounds like a fairly trivial thing to know how much charge your battery has left. Why not just measure the current in and out constantly, a technique known as Coulomb counting. However, counting is prone to error. If, say, a sensor fails or has a low accuracy or systematic error, the predictions will drift over time. Voltage can be measured and gives an instant snapshot of the state of the battery and is therefore usually used as the indicator of state of charge. But is voltage reliable? No, not really. Voltage has its issues too, and depends on how far from equilibrium the system is. Often what happens is the battery is left at rest and then cells connected to parallel start to equalize their open circuit potentials and current rebalances. The overall charge left in the system is still the same, but the voltage at rest has relaxed closer to equilibrium compared with when you switch the system on. This also happens inside the cell as well as between cells. Voltage also depends on temperature, aging, and also whether you are charging or discharging battery. Hysteresis, swelling and cracking. Another problem with silicon is that the particles swell to around 80% bigger when lithiated compared to the delithiated. This is an issue because this causes stress to the particle itself, which may break up and no longer form an active part of the material and may also impact its surrounding host material, either breaking that or breaking its connection with it. These mechanical effects cause accelerated aging of the cell, where active material inventory is lost more quickly and cell capacity decreases. Alright. This is an issue because this causes stress to the particle itself, which may break up and no longer form an active part of the material. It may also impact its surrounding host material, either breaking that or breaking its connection with it. These mechanical effects cause accelerated aging of the cell, where active mechanical effects cause accelerated aging of the cell, where is lost material inventory. Alright, so this swelling up is bad. You get that. Fortunately, making the particles smaller helps both with the voltage hysteresis and the effects of swelling. It also increases the active surface area per unit mass of the silicon, and this helps lower the losses associated with the reactions in the battery. How do I know all this? You might wonder. Well, there is a certain amount of intuition to these things, and I have a PhD. Several more subsequent research in electrochemical system. That's what I should have said. I don't have much knowledge about electrochemical systems. But the main reason is that these systems can be explored, tested, evaluated with computational simulations. Oh, that's very interesting. Alright, he's giving us some graphs. Pi BA MM. Let's look at some cool things you can do with simulation to help debug your battery problem. Pi BA MM is open source and written in Python. That's the Pi bit. The BA MM stands for Battery Mathematical Model. First off, what's going on inside when I charge and discharge, and why is my voltage changing the way it does? Which physical processes and their related design features have the biggest effect on the voltage? Alright, so Pi BA MM, you get a lithium ion DFN. From the parameter values is Chen. Okay, what did it say? Battery mathematical model experiment. You name it. You rest. I feel like I'm missing something here. Maybe these are just parsed later. Simulation. Pi ram the simulation. Get the model. Experiment. Oh no, I don't think it's just that. Parameter values. Parameter values are Chen 2020. So this is probably something that was okay. Let's poke around this a little bit. Pi battery mathematical model. Here we go. It's nice of these guys. I didn't know even this existed. Anyways. Alright. This looks like a convenient effort. Our mission is to accelerate battery modeling research by providing open source tools for multi-institutional interdisciplinary collaboration. Broadly, Pi BA-MM consists of 1. A framework for writing and solving systems of different equations, a library of battery models and parameters, and 3. Specialized tools for simulating batteries, specific experiments, and visualizing the results. Together, these enable flexible model definitions and fast battery simulation, allowing users to explore the effect of different battery designs and model assumption under a variety of operating scenarios. Alright. Negative particle surface concentration, negative electrode potential, electrolyte. Let me just make this bigger. Alright, did it change? No. Didn't. Okay, so I'm just gonna read it. Electrolyte concentration, positive particle surface concentration, micro, that's not micro, is it? I was right, that's micro. Time going from 20 minutes and 10 minutes of discharging. Current is 10, then it goes 0, and then voltage is going down, and then goes back up. Interesting, okay. Alright, here we can clearly see the big difference in voltage when we stop discharging the battery and start testing. But what exactly is going on here? A useful feature of Pi BA-MM is to split the voltage into its constituent components known as overpotentials. You have the ideal potential of the battery for a certain state of charge when everything is in equilibrium, the open circuit potentials OCP, and then you have all the voltage losses associated with the things not being at equilibrium. Okay. Open circuit voltage, particle concentration over potential, reaction over potential, electrolyte concentration over potential, ohmic electrolyte over potential, ohmic electrode over potential. There we have this little model. Not all of these are doing that, but like this has an elbow kind of thing to it. Okay, but anyways, we get the gist of it. Just continue. How we can immediately learn a few things. A large portion of the change in voltage of the cell is just the open circuit voltage changing as a function of lithiation. System of charge. So see the state of charge. State of charge, while other processes are certainly significant. At the point that the current stops, the voltage relaxes a great deal almost instantly. You can see the green reaction over potential, purple ohmic and brown ohmic electrode over potential go from being thick sections to disappearing. This makes sense as these processes are all related to current and ion transport. The orange and to an extent the red concentration over potentials are slow to disappear, which means that ions are still moving in the system when no reactions are taking place, and this is due to build-up of concentration gradients inside the active solid and electrolyte. The electrolyte loses due to concentration over potential during discharge are fairly sizable, around 100 millivolts, but they disappear much faster than within the active material, meaning that diffusion is much easier in the electrolyte than within the solid. Okay, okay, so you got this small guy, and the parameter values are this guy, which I kinda see where you get it from. Pi BAM parameter sets. Okay. Provides predefined parameters for common chemistry as well as a growing set of third-party parameter sets. Class parameter BAMM parameter sets. Dix like interface for access and register. Okay. Okay, let's looking at this third-party parameter sets, bundled parameter sets, lead acid parameter sets, parameters for BBOXX lead acid cells from the PayPal, Sulzer, and everyone else. Chen 2020 parameters for an LG M50 cell from the paper Chen. Okay. Acre and these things go on. Interesting. Alright. We're here. The electrolyte loses due to concentration over potential during discharge are fairly sizable, around 100 millivolts, but they disappear much faster than within the active material, meaning that diffusion is much easier in the electrolyte than within the solid. We can inspect the concentration profiles in both solid particles and the electrolyte to confirm these findings. Below are 5 snapshots at the start of the rest period and afterwards. Okay, so plot, quick plot. Get this from up here. From somewhere. Yes. Where's this? Okay, that has never been used anywhere, but just, Okay, I guess we put a blind eye on this. We keep going. X average negative particle concentration, X average positive particle concentration, electrolyte concentration, X average negative particle concentration, X average positive particle concentration, electrolyte concentration, X average negative particle concentration. Okay, so seems like the particle concentration of the ions is very important. And these graphs are all about it. And electrolyte concentration, RRX. Oh, I mean, this could be the three different things he's trying, right? Okay. The concentration in the positive particles is still not equal as a function of radius. We can intuitively guess then that changing some feature of the positive particle may have some effect on the relaxation behavior of the cell. Let's see what the current positive particle radius is and where changing this value has a significant effect. 5.2 to the power of negative 10 to the negative 6. Parameter values: positive particle radius for M. Not M. Oh, wait. Okay, so these are just strings, my bad. But seems like they go somewhere. Okay. My bad on that one. Then we have some changes. These blue dotted lines. X average negative particle concentration, X average positive particle concentration, electrolyte concentration, X average negative particle concentration, X average positive particle, oh come on, electrolyte concentration. Okay, and then we go, now the contributions of the positive solid particle to the voltage at rest is resolved much more quickly than before. This is because the smaller particle size allows for faster diffusion of lithium ions in and out of the particle. This is a good example of how the model can be used to investigate the effect of different parameters on the performance of a battery. This is just one example of how to use modeling to debug your battery problem. Pyre has also many other examples, including one on modeling hysteresis in silicon nodes. Also, we can see here a single experiment takes a matter of seconds, and with some of the simpler models only a matter of milliseconds. This helps engineers really better the case of dimensionality. For example, the Ragone plot below, sweeping over some of the common parameters you might investigate changing, contains 6,500 data points, and with each one taking less than 1 second, running one after the other on a single core would take under 2 hours to compute. Already a massive saving compared to weeks with our 1,000 channel cycler lab. Each experiment takes less than an hour in the lab, but we have to prepare the materials and build the cell too. With parallel computing, this number can be cut to less than a minute. Okay. If you like this and how to guide and want to learn more about battery modeling, head to our GitHub page. Oh, so interesting. He's one of the guys behind this, I guess. Is he? How can I see who are the 3 people? Okay, that's great. Alright. So let's just reiterate over what we learned. Oh, that's just the figures, my bad. basically is saying there is this module pi BAMM, which is this, that you can use and basically mess around with these batteries, figure out something that works. And oh, you can also have it run parallelly, which is a big thing in my opinion, because he said if we could parallel it, and then it will go from hours to minutes or even seconds. So there is that. But what do I think about this? So I just have a few questions. Obviously, where did these parameters come from? How are they a good representation of the real world? What else? Let me just check something. Oh, ouch. I guess now you have my voice better, but if it's just too much, turn it down a little bit. So yeah, where do the parameters come from? How are they a good representation of what the real world is? I guess they're just recorded values of the labs, but how is it, and what did you get out of this? Didn't quite get what you got out of this. So just one example, another contribution of addresses was a more requirement, but this is because the smaller particle size allows for faster diffusion of lithium in and out of the part. This is a good example of how the molar can be used to investigate. Okay. So he changed the thing to labels, big particles, small particles, and there. Yes, I realized that. So he changed the positive particle radius to this, some crazy small value. And then what he figured out was that the average positive particle concentration improved. Average positive particle concentration improved, and but the electrolyte concentration didn't change. This didn't change. But he made the parts small, so wasn't this artificially being bigger? I would think so. Not sure. Not 100% sure. But yeah, he went through this voltage hysteresis, and then he took us to the swelling and cracking. For sure, making the particles smaller helps both the voltage hysteresis and the effects. It also increases the active surface area per unit mass of silicon, and this helps lower the losses associated with reactions in the battery. How do I know all this, you might wonder? Well, there's a certain amount of intuition to these things. I have a PhD, and so most of them. The main reason is that this system can be explored and tested and evaluated with computational simulations. Okay, and then he tried it. Basically, which may break up and no longer form an active part of the material, and also may impact its surrounding host material, either breaking that or breaking its connection with it. These mechanical effects cause accelerated aging of the cell, where active material inventory is lost more quickly and cell capacity decreases. Okay. So the article started with, so high power versus high energy. Then the silicon stuff. After the silicon stuff, we have your Python MA, BA, MM. And then from there, I believe these should have changed, right? Sweep. Specific energy watt hour per kilogram. Specific power watt per kilogram. Alright, okay. Concentration of the positive particle. Okay, so that's just the concentration of how much you have in the electrode. And everything is in a okay. So yeah, the voltage hysteresis, the empty and not emptying summation goes for this to here to this, and then 25%, 75%. The plate model, what is plate model? Is that a thing? Yeah, plate model. It seems to be something. It's in Science Direct. Modified plate model for model. Why is this so bright? For modeling voltage hysteresis in lithium-ion cells. First order abstract. Okay. Lithium-ion cells share anode material like graphite or silicon exhibit a charge direction dependent voltage hysteresis. In literature, several approaches exist to model this effect. This paper aims at showing modifications to the so-called plate model. It will be shown that the specific slope of the transition between charge and discharge OCV curve can be linked to the slope of the OCV curves themselves. This leads to a significant reduction in measurement and parameterization time. Furthermore, this paper features the application of the improved model to composite electrodes, the separation of the contributions of graphite and silicon. Okay. It's a plate model. Let's see what it looks like. Okay, sure. It's way more beautiful than what I thought, but sure. Seems to be a known thing. This was also the other guy's German system plate. I'm not even sure what I'm looking for. Okay. So yeah, basically what we can understand is you have these tools. If you're researching batteries and there are data available that helps you compute, and then if you have an accelerated chip like your GPU, then you can basically run crazy amount of simulation and basically guide your research in a way that you don't need to brute force every possible thing, which makes sense. I agree. I totally agree. Yeah, I feel like this is good. This is a very short article. I will probably make subsequent videos about batteries and new research areas in batteries. So that's it for this video. Thank you for watching.